In many programming languages, you don't have to think much about stack and heap. However, in a system programming language, such as Rust, a value may behave differently depending on whether it is in a stack or a heap. This concept's form is the basis of the ownership. Therefore, it is important to master this subject. Stack and heap are memory segments that your code uses while running. Of course, are structured in different ways. Stack, as the name suggests, keep values stacked on the top of each other, and you can think of the working logic as if you were creating a stack of books. When building a stack of books, you put the books in the order you received them. With the same logic, you remove the top books in the order you get them in order to reach middle or lower book without knocking them down. This is called last in first out. Adding data is called pushing onto the stack, and removing data is called popping off the stack. The data contained in the stack must have a known and fixed size. Data that are unknown and changeable at compile time kept in the heap part of the memory. The values in the stack are stored sequentially. To represent operations in our main function, when I create a variable called radius, which you will remember from our previous lessons, a place whose area is known on the stack is actually allocated and the value is kept in the allocated place. When we move to the next line, our function is executed. Let's open our function in detail. Let's assume you have defined a variable type char in our function. Since the values are processed sequentially, the appropriate R above the last variable is allocated to the variable C, and its value is assigned. With the same logic, a place suitable for its size is allocated to the next array, and values are created in order within itself. Subsequently, other operations within the function take place. After the entire function is executed and its scope is finished, the last in, first out principle is applied. Thus, the array is dropped first. Then the previous defined values in the function are dropped and the scope of the function is finished. But the data on the stack has dimensions known at compile time. The heap section is used to store values with unpredictable dimensions, such as receiving data from the user. If we explain this again from the example of the book, in a large library, suitable places are reserved for each book or encyclopedia series. Values with different data types and size are placed when there is suitable free space in the heap region. This event is called memory allocation. There is also a pointer on the stack that indicates where the allocated memory is. Since the pointer has a known fixed size, you can store the pointer in the stack, but when you want actual data, you must follow where the pointer points. If you say heap can receive data of unknown size, why don't we design all the memory accordingly? I should mention that heap works slower than the stack part. Accessing data in the heap is slower than accessing data in the stack because you have to follow a pointer to get there. Just like searching for the book you want in the library. The librarian tells you the locker and shelf code of the book, but it takes some time to look for it. Moreover, stack never has to look for a place to store new data. This location is always at the top of the stack. Allocating space on the heap requires more work because the allocator must first find a large enough space to hold the data and then bookkeeping to prepare for the next allocation. In our example, the areas shown in red are represented as filled areas and non-colored areas are represented as empty parts of the memory. When you create a variable of type string, a suitable field is searched in the heap region and the value is placed after this field is found. Similarly, the box smart pointer is used to allocate values on the heap.